Now, in preparation for your survey project, we're going to talk about sampling. What is a sample? Why do we take samples? What is sample data? What is population data? Now, when we talk about quantitative methods, there are really two types of data. There's the population, which is essentially the entire set of cases. Example of this would be taking a census. We want information about everybody. However, taking a census is very expensive and takes a lot of time. So that's why people work with samples, which is a subset of cases. And as we'll find out, it's usually enough to take a sample of 1,000, even if you have a population of 200 million. The sample ought to be representative, look similar to the overall population. This can be ensured if we have a random sample, not if we have a convenience sample. And why do we take the sample? Because we want to make an inference from the sample to the total population. We want to draw conclusions about the total population from the sample. So in the sample that I took online, most of you spoke Urdu as your native language at home. So one could infer that this is the case for all FC students, if the sample of my political science students is representative of the entire FC college population. So in order to make an inference, in order to draw conclusions, we have to make sure our sample is representative. So here I just want to quickly illustrate what the difference between a random and a convenience sample is. A random sample is going to be representative. So here we've got this larger population represented by this cube, and I'm taking a smaller cube out with a similar pattern because it's representative of the overall population. So that sample I took is going to give us a pretty good picture of the population as a whole. A convenience sample is by definition non-representative, and so there's no guarantee that the sample I took is going to look like the overall population. In this case, it's a cylinder that doesn't have the same pattern, just to represent the fact that it's not necessarily representative. All right, let's assume you've taken a representative sample. Suppose you want to find out about the average monthly income in a population. You get a representative sample and you find it's 50,000 rupees per month. Now, how do you know you can trust this? Well, this is where the central limit theorem comes in. We're not going to discuss it in detail, but I'm just going to conceptually briefly discuss it. The central limit theorem argues that if you have a population with a particular mean and variability, that means the average income is going to be something, and there's going to be a range from the lowest to the highest income. Well, we don't know that necessarily exactly what that is. But if we take an infinite number of representative samples that are representative of the population are sufficiently large, then the distribution of these sample means will cluster around the real population mean in a normal distribution. So if we take an infinite number of samples, of course, practically we never do this, but let's suppose in theory we can do it, then the results should cluster around the real average, the real mean, in a normal distribution. And we'll talk about what a normal distribution is. Okay, so let's assume that we could take an infinite number of samples in order to find out what the average monthly income of a population is. The results of the mean of each sample, taken infinite number of times, should approximate that of a normal distribution. A normal distribution, as you can see there, looks like a bell curve. It represents a bell curve, which means that the mean, the median, and the mode are all the same. Furthermore, the results are going to cluster as a result around the middle. So 68% of all samples, of all sample means will cluster within one standard error of the mean. 95% of all sample means will cluster around 2 standard errors of the mean, and 99% of all sample means will cluster within 3 standard errors of the mean. We're not going to discuss precisely what the standard error is, but essentially it depends on the sample size. The larger the sample, the closer a standard error will be. The smaller the sample size, the further it will be from the mean. In this case, we would expect most results from samples about average monthly income to cluster around the real monthly income, so 50,000 rupees a month. This is where the concept of confidence interval comes in. If we take an infinite number of samples, then 68% of all results should be within plus minus 1 standard error from the mean. So if the real mean is 50,000 rupees per month, 68% of all results should be within plus minus 1 standard error. What exactly the standard error is depends on the sample size. But 68% generally is not good enough because 32% of the data is outside of the range. If we go plus minus 2 standard errors from the mean, then we get 95% of all data within that confidence interval. So 95% of all results, as you can see on the bell curve, 95% of all results would be within those 2 standard errors. We call that the rule of thumb of 2. Usually that's good enough for researchers. We can even gain more confidence if we go plus minus 3 standard errors from the mean, over 99%. While we can be sure that over 99% of the results are within those standard errors, usually plus minus 3 standard errors is too big of a range. And so people prefer the rule of thumb of 2. But again, how much the confidence interval actually is depends on the standard error, which in turn depends on the sample size. Let's use an example to illustrate this. Plus, I always wanted to be next to the Donald, so here's my chance. Presidential approval rating is very important, particularly now in the election season. Let's suppose that the real approval rating of Donald Trump in the population in America was 43%, which is probably not that far from the truth. And if we took an infinite number of representative polls, then the sample result should cluster around this 43% in a normal distribution as a bell curve, which means the mode, the median, and the mean would be the same, would be 43%. Now, let's suppose, based on a sample size of 1,000, we've taken one sample, the standard error is 1.5%. So if we go with a confidence interval of 1 standard error, we could be confident that 68%, we could be 68% confident that the real result is within plus minus 1.5% of 43%. So either 41.5 minimum or 44.5 maximum. That's a pretty tight standard error, but we can only be 68% confident that the result actually is within that framework. That's generally not good enough, as I mentioned before. 32% of the results could be outside of that. In other words, our sample could just be a blip that is not representative of the whole. So let's go with a rule of thumb of 2. We could be 95% confident that the real result is within plus minus 3%, which is 2 standard errors of 43%. So from 40% to 46%. Now, if we want to be even more confident of the results, more than 99% confident, we would use the confidence interval of plus minus 3 standard errors. In that case, it would be plus minus 4.5%. So the minimum actual mean would be 38.5%. The maximum would be 47.5%. Now, that range is almost too big. It's not particularly useful to know that Donald Trump's approval ratings between 38.5, which is really, really low, and 47.5, which is actually half decent. So the rule of thumb of 2 is generally pretty good. We'll go with that one. We can be 95% confidence that the result is between 40 and 46%, if, of course, the standard error was 1.5%. Now, as I mentioned before, sample size is directly related with standard error. We want to keep that standard error as little as possible, and so we want to increase the sample size as much as possible in as far as it's economically useful and we have time to conduct that many surveys. Now, the previous example, a sample of 1,000 got us a 95% confidence level that results were within plus minus 3% of the 43% approval rating. This was based on a sample size of 1,000. Now, the standard error is sensitive to the sample size. So let's suppose we don't have that much money to do a survey of 1,000, so instead we do a survey of 400 people. Now, if we had a sample size of 400 people, we could get a 95% confidence level of plus minus 5%, still using the rule of thumb of 2. But the standard error has now increased, and so a 95% confidence level will get us only plus minus 5%. So we would only be 95% sure that the results are within 38 or to 48%. That's too inaccurate to be of any use. So we want to increase that sample size. Now, what if we say, well, we want to get even more accurate? So we increase the sample size to 2,500 people, 2,500 people. And then we'll have a 95% confidence level that the results would be within plus minus 2% from 43. Now, that's more accurate than the sample of 1,000, but probably not enough to justify the costs of conducting an additional 1,500 survey interviews. So this is why that sample of 1,000 is generally good enough. So in this case, it's pretty typical of a survey. The result is 43%, and we'd have a confidence level of plus minus 3, so we could be 95% certain that the results are within 40 to 46%. Phew, well, that might have given you all a little bit of a headache, but let's talk about something a bit more practical. All of the previous conversation depended on getting a representative sample. But how do we get a representative sample? Well, the answer is through random sampling strategies. Random meaning that any single case should have an equal chance of getting picked. There shouldn't be any bias. So a simple random sampling would be to put the entire population into a bowl, like here the example is of a lottery bowl, and then you at random pick out a particular sample. This can be done in like the example shows in the picture, or you could have somebody stick their hand in the bowl. Nowadays, you have computer programs that can do it for you. Now, another strategy would be systematic random sampling. This may be useful if you don't know, for instance, the total population. So here you take a sampling rule and say, I'm going to pick every third, fourth, or fifth case, and we'll ask them the questions, or I'll pick them and analyze them. This should eliminate bias, because perhaps you only want to survey people that you like or that you think are attractive or have a particular shoe color. But the systematic random sampling rule, picking every third or fourth or fifth person, ensures that you're unbiased. Now, there are two other sampling strategies that are particularly useful to study subgroups in society. So one of them is the stratified sampling strategy. In the stratified sampling strategy, you essentially have a population that's divided into subgroups, and you want to compare those subgroups with each other. So you pick cases from each subgroup, of course in a random way, just as the picture shows. So your overall sample should reflect the overall population, but you pick representative samples, random sample from each subgroup. An alternative random sampling strategy is the cluster sampling. Here the population is also divided into groups, but instead of picking a random sample from each social group, what you do is that you pick the entire cluster and study that. So you randomly pick 1 or 2 or 3 clusters from all available clusters and study them. This is particularly useful if the population is quite dispersed and it's not economically possible to visit all areas of a country, for instance. So then you do cluster sampling, where you only study particular clusters. Of course, The key for this is the assumption that the clusters in society look fairly similar to each other, that each cluster more or less looks the same. So you're taking the entire cluster and studying that. Now, in quantitative research, getting a representative sample is very important. But sometimes you'll see surveys taken from non-random samples. Oftentimes these are in journalistic sources, could be an online survey, but sometimes scholars use them as well, particularly if they're not necessarily concerned with the overall population, but they're simply trying to compare subgroups, for instance. Now, the most simple non-random sampling strategy is a convenience sample. You just pick people that are the most easily available to you. Oftentimes this is done in exploratory studies when you're just trying to figure out what might be some of the answers that people will give. How can I test my survey questions, and maybe how can I improve them? A convenience sample is useful. Similar to that is the voluntary response sample. This is essentially what I did with the online sample with you guys. I sent it to all of you, although technically it was not completely voluntary, but you just kind of wait and see who's going to respond back. And of course it's voluntarily. And you have no control over who's going to respond and who isn't. Now the snowball sampling is another variation on the convenience sampling. Suppose you need a large number of respondents, but you don't know a lot of people. What you do is you go to those people around you, like in a convenience sample, and then ask them for more context, and then ask their contacts for more context, and their contacts for more context. And this is how you get a larger sample. Now this will not be representative because perhaps you're tapping only into one particular network in society, but still it will give you some insight about that particular network. Then there's purposive sampling. Here, you're not even pretending to randomly pick people. You're actually picking people on purpose. Now we do this in qualitative research because we want to ask questions of particular people. This is when we use purposive sampling. We want to pick particular people because of a particular quality that they have, or some kind of characteristic that they have. Okay, now it's your turn. Assume that you've been tasked with taking a sample of FC college students. Now describe how you would specifically take a sample using the following techniques: systematic random sampling, stratified random sampling, cluster random sampling, or the non-random snowball sampling, the non-random voluntary response sampling. So for each of these sampling techniques, briefly describe how you would go about taking a sample.